Hi, Hola, Bonjour, and Salaam. Welcome to Blueprint Bazaar. In today's video, we are going to build a detailed 3D model of the NVIDIA RTX 3080 GPU from scratch using SolidWorks. This is a complete tutorial where we will go step by step through the modeling process, focusing on how to approach complex product design and break it down into simple, manageable parts. We begin by understanding the overall structure of the GPU and setting up the base dimensions. Instead of jumping into details immediately, it is important to start with a clean foundation by creating the main body using simple sketches and extrusions. This gives us a solid reference for adding all the other features later. Keeping your sketches fully defined and organized at this stage will make the entire modeling process much smoother and more controlled. Once the base is ready, we start building the outer casing. This involves adding thickness, applying fillets, and shaping the edges to match the real design. The key here is to focus on proportions and symmetry rather than perfection in the first attempt. You can always refine details later, but having the correct overall form is essential. Using features like fillet and chamfer helps in achieving smooth transitions and a more realistic appearance. After that, we move on to one of the most recognizable parts of the GPU, which is the cooling fan. Instead of modeling everything at once, we create a single fan by designing the hub and then building the blades using patterns. Circular patterns are extremely useful here, as they allow you to replicate one blade across the entire fan evenly. Once one fan is complete, it becomes much easier to duplicate or mirror it to create the second fan, saving time and maintaining consistency. Next, we focus on adding smaller details that bring the model to life. This includes features like mounting sections, vents, and cutouts. These elements may seem minor, but they play a huge role in making the model look realistic and complete. At this stage, using reference images can help you understand where to place these details and how they should look. The goal is not to copy every dimension exactly, but to capture the visual essence of the design. As the model becomes more complex, maintaining a clean feature tree becomes very important. Naming your features, organizing sketches, and following a logical sequence will help you avoid confusion later. This is especially useful if you need to make changes or improvements to the model. A well-structured workflow is what separates a beginner from a more advanced CAD user. Once the main structure of the GPU is complete, we shift our focus toward refining the model by adding more detailed features and improving overall accuracy. This stage is all about enhancing the design step by step, starting with secondary features like edge cuts, grooves, mounting sections, and ventilation areas. Instead of rushing into complex geometry, the idea is to carefully observe the reference design and gradually introduce these elements using simple tools like extrude cuts, patterns, and fillets. This approach helps maintain control over the model and avoids unnecessary complications. At this point, it becomes important to think about how different parts of the GPU are logically built. Rather than treating it as a single object, breaking it into sections such as the casing, fan housing, and structural supports makes the workflow much more manageable. Each section can be modeled independently and then combined to form the complete design. This not only improves accuracy, but also makes it easier to modify specific parts later without affecting the entire model. As we continue, symmetry plays a major role in speeding up the process. Features like fans, vents, and repeated patterns do not need to be created multiple times from scratch. Instead, tools like mirror and circular pattern can be used to replicate geometry efficiently while maintaining consistency. This not only saves time, but also ensures that the design remains balanced and aligned. Another key aspect during this stage is maintaining clean and well-defined sketches. Many beginners face issues because their sketches are not fully constrained, which leads to unexpected changes later in the model. By fully defining sketches and using proper dimensions, you ensure that your design remains stable and predictable. This becomes especially important when working on complex models like a GPU, where small errors can affect multiple features. As more details are added, the feature tree naturally becomes larger, so organizing your workflow is critical. Renaming features, grouping related operations, and following a logical order will help you stay in control of the design. This also makes it easier to revisit and edit specific features if needed, which is a common requirement in real-world projects. As we move further into the modeling process, the focus shifts toward capturing finer details that make the model look complete and realistic. At this stage, it is important to carefully observe the reference design and identify repeating patterns, small geometric variations, and functional elements that define the overall appearance of the GPU. Instead of trying to recreate everything in one go, the idea is to isolate each feature and build it step by step. This could include refining edges, adding subtle cutouts, and shaping transitions between different surfaces so that the model starts to resemble a real product rather than a rough structure. One effective approach during this phase is to think in terms of layers. Start with the primary geometry, then move to secondary features, and finally focus on micro-level details. This layered workflow ensures that your model remains clean and organized, and it prevents errors that usually occur when too many features are added without a clear structure. For example, once the main body and fan housing are complete, you can begin adding ventilation slots, screw placements, and small design accents that enhance realism. These details might seem minor individually, but together they significantly improve the overall quality of the model. Another important consideration is the use of reference geometry, such as planes and axes. These tools help you position features accurately and maintain alignment throughout the design. When working on complex shapes or angled features, creating additional reference planes can make sketching much easier and more precise. This is especially useful when dealing with non-standard geometries or when certain features are not aligned with the main planes of the model. Proper use of reference geometry not only improves accuracy, but also makes your workflow more efficient. As the model grows, it becomes essential to manage relationships between different features. SolidWorks allows you to create dependencies between sketches and features, which can be very powerful when used correctly. For instance, if multiple features are based on a single reference dimension, updating that dimension will automatically adjust all related features. This parametric approach is one of the biggest advantages of CAD modeling, as it allows for flexibility and quick modifications without rebuilding the entire model from scratch. During this stage, it is also helpful to frequently evaluate your model from different angles. Rotating the model, zooming in on details, and checking proportions visually can reveal inconsistencies that may not be obvious in a single view. This habit helps you catch errors early and maintain a high level of accuracy throughout the design process. It also improves your ability to judge proportions and aesthetics, which is an important skill in product design. Another useful practice is to simplify complex features whenever possible. Not every detail needs to be modeled with extreme precision, especially if it does not significantly affect the visual outcome. Learning to balance detail and efficiency is key to becoming a skilled CAD user. By focusing on the most important features and simplifying less critical ones, you can save time while still achieving a high-quality result. As you continue adding features, patterns become increasingly valuable. Linear patterns, circular patterns, and mirror features allow you to replicate geometry quickly and maintain consistency across the model. For example, if you have a set of ventilation holes or repeated cutouts, using a pattern ensures that spacing and alignment remain uniform. This not only improves accuracy, but also reduces the effort required to build complex designs. At this point, it is also important to ensure that your model remains fully defined and stable. Avoid leaving sketches underdefined, as this can lead to unexpected changes later. Applying proper constraints and dimensions ensures that your design behaves predictably when modifications are made. This is a fundamental aspect of parametric modeling and plays a crucial role in maintaining control over complex projects. Another key aspect of advanced modeling is understanding how different features interact with each other. Sometimes adding a new feature can unintentionally affect existing geometry, especially when working with cuts and fillets. Being mindful of feature order and dependencies helps prevent such issues. If something goes wrong, reviewing the feature tree and adjusting the sequence can often resolve the problem. As the model nears completion, take some time to review the entire design. Look for any missing details, inconsistencies, or areas that can be improved. This final refinement stage is where you polish the model and ensure that it meets your expectations. It is also a good opportunity to clean up the feature tree, rename important features, and organize your workflow for better clarity. All of these steps contribute to a more structured and professional approach to CAD modeling. Instead of relying on random trial and error, you develop a clear process that can be applied to any complex design. This not only improves your efficiency, but also builds confidence in your ability to handle challenging projects. Now, taking a step back from the modeling process, it is also interesting to understand the real-world product that inspired this design. The NVIDIA RTX 3080 is part of NVIDIA's Ampere architecture and was released as a high-performance graphics card aimed at gamers, content creators, and professionals who require powerful GPU computing. It represents a significant leap in performance compared to previous generations, especially in terms of real-time ray tracing and AI-based rendering. One of the standout features of the RTX 3080 is its memory configuration. It comes equipped with 10 GB of GDDR6X VRAM, which is designed to handle high-speed data transfer for demanding applications such as 4K gaming, 3D rendering, and video editing. The use of GDDR6X memory allows for higher bandwidth compared to traditional GDDR6, enabling faster communication between the GPU and memory. This is particularly important when working with large textures, complex scenes, or high-resolution outputs. The GPU itself contains thousands of CUDA cores, which are responsible for handling parallel processing tasks. These cores allow the graphics card to perform multiple calculations simultaneously, making it extremely efficient for both gaming and professional workloads. In addition to CUDA cores, the RTX 3080 also includes dedicated RT cores for ray tracing and tensor cores for AI-based operations. Ray tracing enables realistic lighting, reflections, and shadows in real time, while tensor cores are used for features like DLSS, which uses artificial intelligence to upscale lower-resolution images to higher resolutions without losing quality. Another key aspect of the RTX 3080 is its cooling design. The Founders Edition model introduced a unique dual-fan configuration with a push-pull airflow system. One fan draws air through the card, while the other pushes it out, improving thermal performance and maintaining stable temperatures even under heavy loads. This design not only enhances cooling efficiency, but also contributes to the overall aesthetic of the GPU, which is why it is often chosen as a reference for CAD modeling projects. In terms of performance, the RTX 3080 is capable of handling modern games at ultra settings with high frame rates, especially at 1440p and 4K resolutions. It also excels in creative applications such as video editing, 3D rendering, and simulation, where GPU acceleration can significantly reduce processing time. Software like Blender, Adobe Premiere Pro, and various CAD rendering tools can take advantage of the GPU's power to deliver faster and smoother workflows. Power consumption is another important factor to consider. The RTX 3080 typically requires a high wattage power supply, as it is designed to deliver top-tier performance. This means that proper system configuration and cooling are essential when using such a GPU in a real setup. The card also uses advanced connectors and power delivery systems to ensure stable operation under heavy workloads. From a design perspective, the RTX 3080 combines both functionality and aesthetics. Its sleek metallic finish, angular geometry, and symmetrical layout make it visually appealing while also serving practical purposes such as heat dissipation and structural strength. These characteristics make it an excellent subject for CAD modeling, as it challenges you to replicate both technical and visual aspects of a real product. Understanding these real-world features not only adds context to the modeling process, but also helps you appreciate the level of engineering involved in such devices. When you model something like the RTX 3080, you are not just creating a shape, but also learning how complex systems are designed, optimized, and manufactured. This deeper understanding enhances your ability to create more accurate and meaningful designs in the future. It also trains you to think beyond geometry and start considering real engineering constraints such as heat dissipation, airflow management, structural rigidity, and component placement. For example, the positioning of the fans, the spacing of ventilation areas, and the thickness of the casing are not random design choices. They are all carefully engineered to ensure optimal cooling and performance. When you replicate these elements in your model, you begin to understand how design decisions are influenced by functionality as much as aesthetics. Building on this deeper understanding, it is also useful to look at the RTX 3080 from a more technical engineering perspective, especially in terms of how its internal architecture influences the external design that we model. The RTX 3080 is based on NVIDIA's Ampere architecture, fabricated on an advanced process node that allows a high density of transistors to be packed into a relatively small die area. This enables the GPU to deliver significantly higher computational performance while maintaining efficiency compared to older generations. The internal GPU die contains multiple processing units organized into streaming multiprocessors, each responsible for handling parallel workloads such as shading, physics calculations, and rendering tasks. A key technical feature of the RTX 3080 is its massive parallel processing capability, driven by thousands of CUDA cores. These cores operate simultaneously, allowing the GPU to process large amounts of data in parallel, which is essential for real-time graphics rendering and compute-heavy applications. In addition to CUDA cores, the presence of dedicated RT cores enables hardware-accelerated ray tracing. This allows the GPU to calculate realistic lighting interactions, such as reflections, refractions, and shadows, in real time. From a design perspective, this level of performance requires efficient thermal management, which directly influences the size, shape, and airflow pathways of the GPU housing that we model. Another important technical aspect is the memory subsystem. The RTX 3080 uses high-speed GDDR6X memory, which operates at very high data rates to ensure fast communication between the GPU and memory. This is supported by a wide memory interface, allowing large amounts of data to be transferred quickly. The placement of memory modules around the GPU die on the PCB affects heat distribution and cooling requirements. While we may not model these internal components in detail, understanding their arrangement helps explain why certain areas of the GPU require more cooling and why vents and airflow channels are positioned in specific locations. Power delivery is another critical factor. The RTX 3080 requires a robust power delivery system to handle its high performance. This includes voltage regulation modules and power connectors that supply stable and efficient power to the GPU. These components generate heat and must be properly cooled, which again influences the design of the heatsink and airflow system. The external design often reflects these internal requirements through features like thicker sections, reinforced areas, and strategically placed openings for ventilation. Thermal design is one of the most important engineering challenges in a GPU. The RTX 3080 uses a combination of heat sinks, heat pipes, and fans to dissipate heat effectively. Heat generated by the GPU die is transferred through a thermal interface material to a heatsink, where it is spread out and cooled by airflow. The dual fan configuration in many RTX 3080 designs creates a controlled airflow path that moves heat away from critical components. This is why, when modeling the GPU, attention to fan placement, vent design, and spacing becomes essential for achieving a realistic and functionally accurate representation. Signal routing and PCB design also play a major role in the overall performance of the GPU. High-speed data signals must be carefully routed to minimize interference and maintain signal integrity. This requires precise layout and spacing of components on the PCB. While these details are mostly internal, they indirectly affect the external design, such as the positioning of connectors and the overall dimensions of the card. Understanding these constraints gives you a better appreciation of why the GPU has a particular shape and layout. From a mechanical standpoint, structural integrity is also considered in the design. GPUs are relatively heavy due to their cooling systems, so the casing and internal frame must be strong enough to support the weight without bending or deforming. This is why you often see reinforced edges, mounting points, and rigid structures in the design. When modeling, incorporating these elements adds realism and helps simulate how the product would exist in a real environment. Another technical detail worth noting is the integration of I/O interfaces such as HDMI and DisplayPort outputs. These connectors must be precisely aligned and securely mounted to ensure reliable connections with external devices. Their placement is standardized to fit within computer cases, which imposes additional design constraints. Including these elements in your model not only improves accuracy, but also reinforces your understanding of how products must conform to industry standards. Continuing with the technical exploration, the NVIDIA RTX 3080 is a significant advancement over previous GPU generations because of its combination of raw computational power and energy efficiency. Built on NVIDIA's Ampere architecture, the GPU uses second-generation RT cores and third-generation tensor cores, which drastically improve ray tracing performance and AI-powered workflows. These cores enable features like real-time ray trace shadows, reflections, global illumination, and DLSS, deep learning supersampling, which intelligently upscales images to higher resolutions without compromising performance. From a modeling standpoint, understanding these internal functional components provides context for why the GPU is designed with such attention to cooling, component placement, and airflow. Each fan, vent, and heat pipe is purposefully positioned to manage heat produced by these highly parallel processing units. The GPU die itself is a marvel of modern semiconductor engineering. It contains billions of transistors fabricated using an 8-nanometer process node, allowing massive processing density in a compact area. The die is the core computational unit, and its placement on the PCB must be optimized for minimal thermal resistance and efficient signal distribution. While the die is internal, in CAD modeling, this affects the surrounding structure, such as the heatsink baseplate, fan positioning, and case thickness. A designer modeling the RTX 3080 needs to understand that these seemingly aesthetic features are actually highly functional. The VRAM system is another critical area. The RTX 3080's 10 gigabytes of GDDR6X memory modules are distributed around the GPU die to ensure short, high-speed communication paths. This reduces latency and maximizes bandwidth, which is crucial for 4K gaming, 3D rendering, and high-fidelity simulations. In terms of thermal design, memory chips also generate heat, albeit less than the GPU die, so they are strategically located near cooling channels and airflow paths. This explains why, in CAD modeling, certain areas of the card have vents, cutouts, or raised sections to allow airflow over these heat-generating components. Power delivery is another essential aspect. The RTX 3080 requires a powerful and stable supply to achieve peak performance. This is handled through multi-phase voltage regulator modules, VRMs, on the PCB. These VRMs convert power from the PSU and regulate voltage to the GPU and memory. Each VRM produces heat, necessitating additional thermal management features such as heat sinks or thermal pads. When modeling the GPU, the power delivery system may influence not only the PCB layout, but also the overall thickness and placement of the cooling system. Designers need to account for these real-world constraints to create an accurate and believable model. Thermal engineering is arguably one of the most critical considerations in a high-end GPU. The RTX 3080 employs a combination of heat pipes, vapor chambers, and high-conductivity materials to move heat away from the GPU die and VRAM modules. The dual-fan system and shroud design are engineered to maximize airflow efficiency. Fans are oriented to push air through the heatsink fins and out of the case, creating a controlled thermal path. When modeling the GPU, these fans and vents are not purely decorative. They are functional representations of these engineering choices. Accurate CAD modeling of these features requires understanding airflow patterns and the purpose of each opening or grill. From a structural perspective, the GPU must endure physical stress during installation and operation. High-end GPUs, like the RTX 3080, are relatively heavy due to their large heat sinks and multiple fans. Therefore, the casing and internal frame are reinforced to prevent bending or warping, which could compromise thermal contact with the GPU die and VRAM modules. In CAD, this translates to including realistic thicknesses, fillets for strength, and mounting features that reflect actual hardware constraints. These considerations are crucial for creating a model that not only looks realistic, but also makes sense from an engineering standpoint. Signal integrity and PCB layout are also highly relevant. High-speed memory and GPU signals are sensitive to noise and interference. This requires careful placement of components and routing of traces. Connectors for HDMI, DisplayPort, and PCIe must be positioned precisely to maintain compatibility with standard PC cases. These constraints influence the external form factor, including edge lengths, connector cutouts, and overall thickness. Understanding these elements helps CAD designers appreciate why the GPU has the shape it does and why certain features, like notches and gaps, exist. The exterior aesthetics of the RTX 3080 are also influenced by thermal and structural engineering. Sharp edges, angular surfaces, and vents are all designed to improve airflow and heat dissipation while giving the card a modern and aggressive look. Fillets and chamfers are not just visually appealing. They help reduce stress concentrations in the metal parts and improve manufacturability. Including these details in your CAD model adds authenticity and demonstrates an understanding of design for manufacture principles. Another technical consideration is weight distribution. GPUs must be balanced within a computer case to prevent sagging over time. NVIDIA often uses a combination of metal and high-strength polymers in the casing to achieve a balance of rigidity and weight reduction. In CAD, modeling these structural elements accurately helps convey the functional design of the card and allows for visualization of how it would sit on a motherboard. This is why including the backplate, support brackets, and connector reinforcements in your model is essential for realism. The cooling system also interacts with software performance. RTX 3080 cards adjust fan speeds dynamically based on GPU temperature and workload. This means the fan size, blade angle, and shroud design are optimized to move maximum air efficiently while keeping noise levels low. When modeling, the fan blade geometry, spacing, and orientation can be replicated to reflect these real-world constraints, giving the render a technical authenticity beyond aesthetics. Finally, features like RGB lighting, branding, and design accents also have technical reasons. RGB LEDs often require separate wiring channels and power distribution, which influence space allocation and internal geometry. Even small design details like logos, vents, and color accents are considered carefully to avoid blocking airflow or affecting cooling efficiency. Including these elements in your CAD model not only improves visual fidelity, but also demonstrates a professional understanding of product design principles. When all of these elements, GPU die, VRAM layout, power delivery, thermal management, structural support, airflow optimization, and visual design are considered together, the RTX 3080 is not just a piece of hardware, but a highly optimized engineering system. Modeling it in CAD with this knowledge allows you to create a model that is both visually realistic and technically informed. It helps you appreciate the interplay between performance, cooling, structure, and design, and it trains you to think like a professional engineer, where every feature has a purpose and every shape is optimized for function. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.